Hello, welcome to Video 14A. This is Professor Gill and we're going to talk about the basics of milling. So you've all been doing milling in the lab, but let's talk about what is milling, what defines milling. So first of all, in milling, the tool is rotating and the part is either stationary or moving, but it's moving at a slow speed relatively, and the tool is the part that's doing the rotating. Generally, the feed direction is perpendicular to the rotational axis and in either of the perpendicular directions. This is not always true, but it is 90% true. You can do milling where you're feeding in the direction of the rotational axis, but it's called plunge milling and it's not done very much. Generally, there is interrupted cutting. So each tooth on the milling cutter is going into cut and then it is coming out of cut for a little while and then going back in. Because of that, the tools have to have a lot of toughness. They have to have a lot of impact resistance. So as they impact, they won't shatter. It is extremely versatile. The machines and the processes are just everywhere. You see milling all the time. There are two basic types of milling. One is peripheral or side milling, and one is end or face milling. So in peripheral milling, you're milling with the side of the tool, and that side of the tool is parallel to the tool rotation axis. And so there's a picture of peripheral milling where you can see that the rotational axis in this picture is horizontal and the milling surface is parallel to that axis. And then the second is end milling, where the cutting is happening on a surface that is perpendicular to the tool rotation axis. So in peripheral milling, you get these long, smooth sides of the cutter doing the cutting, long engagement lengths. That means that a long section of the tool is engaged in cutting, so you can get a lot of deflection because the forces, if you have a force of cut all the way along this edge that's in contact and it's a pretty long edge, then that can end up being a really large force, and so it has the opportunity to deflect the milling cutter, or it can deflect the part depending on how small your part is. On face milling, you generally have a very short, stubby, stiff tool, and so that's great for really getting a fine surface. You also have a large diameter, so with a large diameter, the cutting speed can be quite high, and without a large RPM or spindle speed. And then also because you have this large diameter, it can often overlap a lot of the surface, and so you get a pretty smooth face. Generally though, the horsepower of the machine, the power of the machine limits the diameter that you can turn, because if you have sort of the same amount of force and energy required to cut the material wherever the tooth of the tool is, if you're way out on a long radius, then the torque is too high and you can't turn it. And so each of these peripheral and face milling is done, certainly, and we will do that a lot as we go through things. But very often we do both at the same time. So we will use an end mill like this, and so this is some of the confusion of everything, is that this is called an end mill when it is just sort of one stick like this, and the end mill is often used for side milling, for peripheral milling, but it also often cuts the bottom of a shoulder or pocket like this. So that is the methods of milling, peripheral and end, or side, peripheral side or end face milling. And then there are two strategies that are often used, and that depends on how do you rotate the part, or I'm sorry, how do you rotate the tool with respect to which direction you're moving the part? Or if the part rotation is generally fixed, then how do you move it past the part? So in this picture, the tool is up here and it is stationary, but it is turning. So it is turning clockwise as shown here. And the part is feeding from left to right on your screen. And so as it feeds across from left to right, you can think about one tooth goes by, and by the time the next tooth hits, starts to cut, the part will have moved a little bit to the right. And so when this tooth starts to cut, it will start on a very thin cut because there's almost infinitesimal thickness right here. And so what happens is, when there's not enough thickness there, the tool will somewhat just rub along the surface, and it rubs along the surface for a while until it builds up enough stress that it can start to shear the material off. And then as it starts to shear the material, it will take a deeper and deeper and deeper cut, and then because the part is continuing to move, it's getting thicker and thicker and thicker, and then when it finally gets to the end, it is a full width chip, and it's going to throw this chip right in front of the cutter. So that is called conventional cutting or up milling. So in up milling, the forces are higher overall. Somewhat that's because of starting with this thin chip and rubbing right along here until you can finally get in and cut it. The deflection is parallel to the cut. So if you can think of this, the force is getting greater and greater and greater, but that force is primarily going to be along the part. So the tool right here is going to deflect a little bit to the right, and so you will get a little bit of inaccuracy with the tool deflecting to the right. The chips are dropped in front of the cutter, and you get additional heat because of the rubbing when it starts out before it can initiate the chip. And it may work better on a machine with backlash. So the common thought is that there's not much impact here because each one of these chips just gradually enters cut. And so if your machine has some looseness in the way that it moves along the X or the Y axis, then this will help with that. The second strategy is called climb cutting, or also called down milling. To me, up milling and down milling are somewhat confusing terms. They come from, this is starting here and going up, but that only works in this picture. And so conventional and climb are better. So in climb cutting, the tool is rotating in the same direction, the axis is still stationary, and now the part is feeding past again. But this time, as the part feeds past and this next tooth comes in to cut, it's hitting right here on this surface. So it's not a gradual entry into the material like we had in the last one. It is a sudden entry. So it whack, it hits, and as soon as it hits it, it's in full cut, and it's taking this big chip, and the forces get smaller, 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 and then it throws them. So the biggest force is right here where it begins to cut. And so it puts this big force onto the part right here at the beginning, and the force is perpendicular to the axis of motion. So the impacts are more severe. The deflection is perpendicular to the cut, and so this big force over here will cause the tool to deflect out a little bit from the part and maybe a little bit back too, but mostly out. It drops chips behind the cutter, which is kind of nice, so it won't run over them. And most CNC tools do better for roughing with climb cutting. Now, you can't always tell. It's really interesting. You can't always predict what's going to happen. So I said that generally a machine with backlash, so an old worn out machine, works better with conventional cutting. But in fact, in the lab, I think most of you, whether you knew it or not, have found that conventional cutting did not work as well as climb cutting. So anyway, I would like you to experiment with both in the lab, and you can see it may vary by the machine and by the cutter that you happen to be using, may vary by depth of cut. There are all sorts of things. It is not a firm and fast rule, but it's something that's easy to try, and so it's good to try it. All right, important milling terminology. So we have feed per tooth, so that is the amount that so we had this tooth start cutting right here, and before the next tooth hits, the part has moved over a certain amount, and so when the next tooth starts, we will have this much material along the top here that has fed over before the next tooth hits. So that's feed per tooth. That's just a dimension measured along the surface of the part. And so the machining feed rate, so machining feed rate is inches per minute, equals feed per tooth, so that's inches per tooth, times revolutions per minute, times in, which is the number of teeth. And the way that the units work out is that in is the number of teeth per revolution. So if you were to take the tool and count around in one revolution, 4 teeth go by, then you get this equation. The depth of cut in this is from the top here to where we are expecting the bottom surface to be. Now remember that that isn't always exactly what is cut. But anyway, so that is the depth of cut, the radial depth of cut. There's also an axial depth of cut, which is in the direction that we're looking along the axis, but this is the radial depth of cut. Okay, some terms that you need to know. Now, as you've started on the mill, I've gone over most of these with you, but we will review them again. So this is a knee type milling machine, which is what we've been using in lab over here on the right. Vertical spindle machine, and so it's called a knee type because of the knee. The knee is this big thing at the bottom that goes up and down on the elevating screw, and it rides on the column. So the large block at the back that has the big dovetail slide is called the column, and the knee rides up and down the column. On top of the knee is the saddle. It looks like a saddle sitting on top of the knee. And then on top of the saddle is the table, which moves back and forth. So the table is the x-axis, the saddle is the y-axis, and then Z is along the axis of rotation all the time. And so that's done by both the elevating screw and then the quill. So the quill is this section right here that can extend out of the spindle, so you use that when you're drilling. This whole thing is called the spindle or the head of the machine, so that includes the quill, it includes the bearings in here, and it often includes the gearbox and the motor. Often this whole section that turns the tool is called the spindle. They have a gearbox at the top, a motor, and then that is all mounted on the ram. So we haven't used this at all in the lab, but these are very versatile machines, and so this ram can extend forward or it can retract back depending on whether you need you need it sticking way out so you can work on a big part, or you need it back in tight so there's not much deflection. Also, the spindle head can rotate in 2 different directions around the ram. It can rotate around the y-axis. It can also rotate around the x-axis, and so they are extremely versatile machines. We don't use it much in lab because once you rotate them, they're pretty hard to line back up. But those are the things you need to know are the knee, the saddle, the table, the column, the ram, the spindle, and the quill. Tooling. When you want to do milling, you have to choose tooling. So the first thing that you would look at in choosing tooling is the diameter of the tooling. If you have large tools, it takes less time to cut the entire surface. If you have small tools, you can get into a smaller corner because that just fits into the smaller corner better. So you have to make that choice. Sometimes you can use 2 tools, one to rough everything out and one to go in and touch up the corners, or maybe you have to do the whole thing with a small tool so you can get the corners that are specified by the designer. And finally, it may be limited by the machine's horsepower and torque capabilities, so you may not be able to turn that really big tool because the moment arm is too big, and so you have to just use a small tool. You choose the length of the tool, so you need it long enough to get to the depth of the features. We've had several parts, especially on the cylinders, where we had to get a longer tool to be able to cut the entire height of the cylinder at the same time. But you want the tool to be as short as possible so that it won't deflect. The next thing that we're interested in is the number of teeth. So the number of teeth, if you have more teeth, you can have a faster feed rate. But if you have fewer teeth, you get a bigger gullet. That is the area behind the teeth, and that is where the chips go. And so a bigger gullet allows for bigger chips, and a smaller gullet, which comes with more teeth, only allows for smaller chips. So if you are doing a material like aluminum where you can cut a pretty big chip, then the common way of approaching that is to have fewer teeth and big gullets so you can have a place to put that big chip. And then if you're cutting a material like steel, then you would have more teeth and you would have smaller chip gullets, and that would work out well. On all of the tools, you can have ground tools like the end mills that we've been using in class, or you can have replaceable inserts. So all of those tools that we've used can have replaceable inserts. If you pay more for the tool originally, it allows you to use the same tool for longer because you can flip those inserts around, use several edges, and then replace the inserts. All right, finally, we have geometry, whether it is a center cutting mill or not. So a center cutting mill will have this edge that goes all the way to the center of the tool. Now, and a non-center cutting has a hole right here in the middle. Why do they put a hole right there in the middle? Why do they not just always go to the middle? Well, if you think of this is spinning around some axis. So the center of rotation here doesn't actually move, and just barely out from the center of rotation just barely moves. It has a very slow speed. And so the cutting right here in the center of the tool is pretty doggone lousy. So we really only use the center of the tool if we have to plunge the tool into the material. And even then, we try not to do it. We try to ramp into the material. We try to drill a hole first and then follow the hole in. You're doing that on the bases, some of you, where we're drilling a hole first and then we're plunging the tool over that hole. Remembering, it's really important to remember that there is no rotation right here and there's very slow rotation out here. So the cutting forces are very high right here in the middle of the tool, and they will mess with things. So very often we use non-center cutting tools, and that prevents any cutting from going on in this area. It keeps the cutting forces lower, but if you try to plunge one of these tools, it will not go well for you. Another way that we can have different geometry is by the shape of the end of the tool, and there are lots of shapes. So the one that we've been using the most in class is the flat nose tool, which has square edges. There actually is a little tiny radius out here on the corner, but it's really, really small, usually 2 thousandths or 5 thousandths or 10 thousandths of an inch. There are ball nose tools, which come all the way down and have a constant radius all around. These are used a lot in 5-axis milling because you can mill with every side of the tool equally well. There are some challenges with that because, again, this little center section right here at the end isn't really rotating, so you have to deal with that a little bit. And then there are bull nose. So a bull nose is like a square nose mill, except that these radius are a lot bigger. They're often like 30 thousandths or 60 thousandths. So one thing that happens is on a flat nose tool, these little corners will break off. That's usually the first failure point, is that those corners go. And so the bull nose just already radiuses those corners before you start, and so you have a lot of strength there because it's a nice round radius instead of a little tiny sharp edge. There's a chamfer cutter, which you use to put a chamfer on top of a part. That is similar to the corner rounding tool, which has the inside of a fillet in it, so you can round the top corner of a tool. Both the chamfer tool and the corner rounding tool require really careful setups of the tools to be in the right location to have a smooth transition through them. And then there's a keyway cutter. So if you need to cut a slot in a tool, you would go in with a flat nose tool first and cut out a slot, a vertical slot, and then you could feed this through it from the end and cut this keyway down below. And so an area when that's been done, where that's been done, is the keyways that are in the table of the milling tools. All right. So finally, the last thing you have to select on tooling is to select the materials and coatings, and that is from the last lecture, so we won't go over that again. Finally, the axes of a mill. So in a mill, well, let's start with X. X is defined as the longest axis in most mills, so that would probably be crosswise in this mill. It's a little hard to tell. This is kind of a funny looking mill that I picked. So anyway, it's usually crosswise, so the longest direction of travel is X. Z is the axis along the rotation of the spindle. So wherever the rotation of the spindle is, whether that's vertical in a machine like this or horizontal in a different machine, Z is along that axis. And then Y is the final axis. So it's the shorter dimension but perpendicular to the spindle of the tool. If you have, so there's X, Y, and Z, and then if you have rotaries, A is the rotary around X, B is the rotational around Y, and Z is the rotational around C. Some tools will also have UVW, which are rotations. Sometimes that's put in because if the rotations are on the spindle, they'll be ABC, and if they're mounted on the table, they'll be UVW. It just depends on the nomenclature of the machine that you're using. All right, so that is milling. We will talk about turning in the next video. Thanks for watching.